Hi, this is a demo of One Small Step. What you're seeing here is a simulation of the Apollo 11 mission, starting at the Kennedy Space Center, just moments before the Saturn V's launch.
4 minutes, 15 seconds. The test supervisor now has informed launch vehicle test conductor Norm Carlson you are go for launch. From this time down...
The environment's powered by CesiumJS, which is an open-source JavaScript library designed for creating dynamic 3D globes. It's great for visualizing geospatial data, like the Earth and Moon, with high accuracy. We chose it because it handles time dynamic data really well, which is important for showing how the spacecraft moves and orients itself throughout the mission. It really brings the simulation's calculations to life.
3 minutes, 45 seconds and counting. In the final...
Now to make it more immersive, we also synchronized the audio using Howler.js. Howler is a great audio library for the web. We line up specific clips, mission control chatter, engine sounds for different flight stages. For the mission control chatter, there was an online journal which journaled the Apollo 11 mission, and it also included the timestamps and the audio files, which was very handy.
As you're seeing here, we are running a real-time emulation of the Apollo guidance computer, the pioneering system that guided astronauts to the moon. This Rust-based emulator replicates the AGC's 15-bit architecture, executing the original Apollo software like Retrieve 50 at cycle-accurate speeds. The CPU core fetches instructions from ROM, decodes them into operations like arithmetic or control flow, and updates registers and memory dynamically. Over here, the disk key interface is replicated by TCP. It simulates the astronaut's display and keyboard, translating key presses into interrupts. Behind the scene, the memory subsystem handles bank switching, toggling between RAM and ROM, while peripherals like down-drop system stream data. To maintain historical accuracy, the emulator is synchronized using precise time loops and thread-safe channels to coordinate peripherals and CPU without blocking, ensuring concurrency. While the core functions are implemented, this is not a complete emulation of the Apollo guidance computer.
At the 50-second mark in the countdown, guidance system goes on internal at 17 seconds, leading up to the ignition sequence at 8.9 seconds. We're approaching the 60-second mark on the Apollo 11 mission. T-minus 60 seconds and counting. We passed T-minus 60.
Now, a really cool part is how this interacts with an emulation of the Apollo guidance computer, or AGC. We're using WebSockets to connect the front end to a Node.js backend, which keeps an eye on the AGC's emulator output. Just like in the real mission, the simulation waits for confirmation that the correct flight program, in this case, Saturn V, is loaded into AGC before it allows the launch sequence to proceed.
Ignition sequence starts. 6, 5, 4, 3, 2, 1. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
And there we have it, liftoff. The Saturn V begins its journey.
Now we'll be going through the most important parts of code. Firstly is the include transmute macro, which loads Apollo era ROMs into custom macro, which directly casts binary files into a static 15-bit array. This is a zero-copy approach. The disk key display in diskkey.rs runs on dedicated threads. Key presses are captured via TCP and sent to CPU via crossbeam channel. The AGC reg struct in registers.rs manages fixed blank and erasable blank values, dynamically remapping memory access. This allows for the emulator to switch between ROM and RAM segments. Functions like adjust overflow in utils.rs marks the 15 bits and handles sign extensions, ensuring the emulator behaves identically to the AGC's custom ALU, even on modern 64-bit hardware. Together, these components create AGC's hardware-software interface with cycle accuracy, bringing 1960s engineering with modern Rust safety.
A key part of the launch phase is the gravity turn. The rocket initially climbs vertically, but then it needs to start pitching over horizontally to gain orbital velocity. This Python function calculates the target pitch angle. It's not just a fixed turn, the angle changes based on the rocket's altitude and time since launch, gradually using Earth's gravity to help bend the trajectory towards orbit. Just like the launch, the lunar's descent isn't arbitrary. It follows a calculated guidance profile. This Python code defines how the lunar module's pitch angle and engine throttle should be adjusted. It looks at the current altitude and velocity to manage the descent rate, ensuring the lunar module brakes correctly and targets the landing site in a controlled manner.